Good. So obviously we're still working out the kinks here. We haven't had an in-person seminar in a while, but it's great to see, we have about 20 people in the room here, 25 people in the room here, and a lot more people online. We're very pleased today to welcome Venkatesh Salagrama from Boston University. He's not only a visiting speaker, this is doubling as an IEEE Distinguished Lecturer event. Well-deserved honor for Venkatesh. So he's, so like I mentioned, he's a professor at BU. He's also a data science fellow there, and he's currently on leave working at Amazon right now, where he's just telling me about all the sort of exciting projects he's starting to supervise there as well. So if you've spent any time in kind of the mathematical signal processing communication information theory segment of the world the past 20 years, you probably know who Venkatesh is. His imprint has been very wide. So he's worked in information theory. He's made contributions to online decision and control. He's made contributions to signal processing. He's made contributions to machine learning. And today he's going to tell us something of like a mix of between all those with his recent work on federated learning. So we're very happy to have him. But before we do, I want to give the microphone over to Wendy for a second. She's going to tell us a little bit about IEEE Atlanta.
Sure. So I'm the chair of the Atlanta IEEE Signal Processing Chapter. This is also our first in-person event since January of 2020, when the pandemic began. So we're very pleased to get together with everyone here at Georgia Tech, the students and faculty, and Dr. Salagrama as well. We always encourage students to join IEEE. You can join as a student member. There's a lot of opportunities to meet people and network and learn about different areas in signal processing. So please do so, or you can talk to me if you'd like. So I think Justin, you did a wonderful job of the introduction here. So I'll hand it back to you.
Great. Okay. So without further ado, Venkatesh.
All right. So that's I have to unmute and start video. Cool. All right. Thank you, Justin, for a very kind introduction. And thanks, IEEE, for in making this possible. I do have a few slides on IEEE, but if you do not know what IEEE and SPS is, I'm happy to talk about it after my talk. Rather than right now. Okay, so today what I'm going to talk about is customizing federated learning to the edge. And this work came about by a wonderful team of people. Al is my graduate student, and Rui Zhao is my graduate student. The rest of them were at the ARM ML research labs. This field, I guess, ML is so fast moving, none of them are anymore in this lab anymore. All of them have left since a year. Okay. So the content of this presentation is in three papers. One is in. I think I didn't share your screen.
I did not share my screen. Share. Again, I have to sign in?
No, don't have to. Oh, sorry.
Cancel.
And go to the top right. Oh, okay. Oh, yeah. Or is this the first time? All right, now try again. This one, yes. Okay, so like I said, the content of these, should I repeat myself again? I think self-explanatory. So the content of these papers, the content of this talk is in these 3 papers, and you can look at them if you're interested. Okay, so what I want to do, maybe many of you might not have heard about, you might have heard about federated learning, but kind of not given it much attention. So I want to sort of set this up in a more introductory fashion. And please ask me questions if you have any questions along the way. So why federated learning, right? Fundamentally, if you look at deep neural network training, it requires a lot of data to train it. And at the server, you have a lot of compute. So if you have a lot of data at the server and a lot of compute, the server has a lot of compute, you can train a good deep neural network. Now, the issue is a lot of the data is spread across millions of low compute edge devices, right? So abundant data across millions of low compute edge devices, it's not on the server, and you do not have massive computation. So fundamentally, the question that federated learning is trying to ask. What does that mean? What am I supposed to do?
So sorry. Sorry again.
Okay.
Cool. No problem. No problem. So basically, you have conventional deep neural network training. You can train it on the server if you have abundant data and massive computation. Unfortunately, all of the good data is not at the server. It's all at those phones and iPhones and so on that you use. And fundamentally, the federated learning is trying to address this question, how to unlock the power of the edge data while respecting privacy. Okay, so that's the fundamental question of federated learning. How can you unlock the power of data that you possess without sacrificing your privacy? Now, I got stuck. What happened? Did you do something? All right. So the dilemma of edge device users, user has very little data of his own, his or her own. So the user cannot really train in isolation because the performance is going to be very bad. On the other hand, does not want to share or pool data to improve performance. So that's the privacy issue. So on the one hand, cannot live with your own data because that's not enough to train a good model. And if you don't want to share because you don't want to sacrifice your privacy. So basically, federated learning, like I said, is to unlock the power of data with the following constraints. You don't want to share data, which is the privacy. You want to respect device compute constraints, which we are not going to stress too much about, but we are going to stress about user availability. What that means is users don't want to be available all the time. They're available only at certain points in time, whenever their energy, you have full juice on your phone or whatever, or you put it for charging, right? Those are the situations where you are happy to be active. So basically, that is a federated learning problem. So you want to think about this example of federated learning as a running example so that you can keep this in mind. How is this even possible? Okay, in a sort of streaming fashion, for instance. So you have millions of devices with local models in the system. Each device has its own model. And it's a good idea to think about this SMS text that you would do. What would you do here? I don't know whether it's visible, But basically, you have seen what happens, right? You would type out a snippet of your text, and when you type out this text, it gives you 3 options, and you either can select one of those options, or you can simply, choose a different word. So the device does all of this locally because the model is local, and the device learns from it because it's exactly a supervision. If you select one of those words, then you get supervised. If you do not select one of those words, it also gets supervised because it's negative data. So it penalizes itself when you do not get the word, and it gives a positive reward if you get the word. Okay, so this happens all locally, and it is completely private, which is good, not shared. And then the device model, what it does is whenever it is active, it will send that model to the cloud. So whichever is active here, the white phone is active, it will send it to the cloud. And then you have the cloud server, which, with different devices, which transmits model update sporadically. So that's what I mean by there are these 3 white devices. Those 3 white devices are transmitting to the cloud sporadically. All the other devices are not happy to transmit at that point. Okay, so that is how it happens. So now that the server got those models, you would fuse those models in some fashion and transmit that updated model to the devices which are going to be active tomorrow, not the ones may have become inactive. So some other devices come on, and then it transmits to those new devices. Okay, and so on and so forth. That completes the loop. Okay, any questions? Because I think if you understand this setup, it's fine. Yeah, Justin, you had a.
No, I was going to ask. So you mentioned privacy at the beginning.
Yeah.
So where does that come in this example, or you're going to talk a little bit about how that's enforced, or?
The way it is enforced, and this is not the computer science level of privacy. This is a privacy in the sense that your data is never transmitted. The only thing that is transmitted is the model. People have looked at, federated learning after the time federated learning became popular. People have sort of worked on every single thing like differential privacy with federated learning and so on and so forth. But here we are happy with saying if we can transmit the model, we are happy to call that private. Okay, so let me flesh out a bit more. So we have this federated system with various constraints, privacy, which is necessary for every user, but the user also wants lots of data to train on because the user does not have enough data. So yeah, go ahead.
Privacy, the privacy process. Here, you look like a privacy is more systematic.
Yes.
So do you have some comment on how to measure privacy is kind of?
Yeah. So like I said, I was telling Justin, right? We consider not sending data and only the model as sufficiently private.
So you don't have the numbers of how much privacy.
So are you leaking information because you transmitted the model? Yes, strictly speaking, it doesn't satisfy the definition, the CS definition of privacy. But for us, at least the paper that introduced this topic called this private. So that's what this called as private. So what are the constraints? So that's you only send model, you don't send data. You have participation is very small among a massive number of devices, sporadic activity. This is another important thing, heterogeneity. What that means is different devices have different types of data. I might be interested in cars, as another person may be interested in planes and things like that. You have to be able to support the fact that different people have different amounts of different data, not enforcing the fact that everybody has the same distribution. Okay. So this is another thing which we will not talk about in this talk. different people have different devices, therefore computational budgets for different users would be different. So again, the goal is very simple. You want to figure out a model that matches the accuracy of training as though you had pooled data in the central server. So if you could take all the data and pool it in the central server, what is the best possible performance you could get? That is the accuracy you want to match with your federated learning system. So we will look at different types of problems here, but we will only solve one or two problems, okay? Just to give you a big picture of what kinds of problems might be of interest. So here, yeah.
Other question. So when we do talk about different data is there present at different lines, do we talk about these tasks are similar, or do we talk about these tasks to be different, or this data?
Yeah, so when we talk about customization, you will have different tasks for different users. So if I'm interested in airplanes, airplane classification, I just want to build a very good classifier for airplane classification.
So would it be still classification for all the kinds, or it could be some orthogonal task for some of the kinds?
Yeah, so I am interested in airplanes, you are interested in birds, but we still are in a federated system. It still might make sense for us to collaborate, because even though I'm not interested, you are not interested in my task, I'm not interested in your task, there may be a representation which can be shared amongst us, image representation, off of which you can customize to my own, I can customize to my task, you can customize to your task. Maybe I'm not understanding your question, but yeah. So can federated training match accuracy of models trained on pooled data? So that's question number one. And then we want to consider these types of constraints. Why I put a picture of airplane, automobile, etc., is precisely because you asked this question: how does multitask environment work, right? So that is your second question. Different people might be interested in different things, but even though I might not be interested in birds, I may have bird data. So it's worth sharing with you, whatever, to the extent that I have bird data. So how to rapidly personalize to user-specific tasks? So that is the second question you may want to ask. You may also want to ask how to learn in online or streaming scenarios. In fact, as you collect more and more data, Georgia is going through important elections right now. So you might suddenly get interested in some other thing that you were not, a few months back, in which case you will have concept drift. And how do you adapt to these types of scenarios in a federated setting? How to learn in online or streaming scenarios with personalized concept drifts, and so on and so forth, right? So the solution to all of this lies in some sense, we have a solution to all of these types of questions. And our solution, in a nutshell, take-home message is there's something called de-biased training at the local level. So every device, in some sense, rather than optimizing its own task, strictly speaking, it'll optimize a de-biased task. And by optimizing these de-biased tasks and sharing these models, de-biased models, it leads to updates that are, in some sense, globally optimal. Okay, can handle all these types of tasks. So that's the basic message of this one. So let me try to set up the problem. So here is your vanilla federated learning. By vanilla, one means it's not personalized. Okay, still all the other aspects are true. And here, what is happening is that think of a device K, user K, that device has a data set dk, and you can write down a loss. And the loss is very simple. Like I said, you have a text snippet, and Google Gboard or something produces a prediction, and then that's called as the word completion. If the word completion is from the choices of the Google Gboard, then it gets a loss. It doesn't get a loss, otherwise it gets a loss. So you can self-supervise yourself in that manner. And then the global loss is just the sum of these losses. You can get a little bit fancy by putting a weight and so on. I'm not going to mess with that. And so you get a global loss. And then what happens is whoever is active, in this case, the solid red line is active, sends its update to the server. What kind of update can be sent? it can use a previous state it has so far received from the transmitter, from the server, which is called as theta naught. So that is something that is, let's say on a previous round, it got this theta naught, and it has its previous model, which is theta k. It can combine these two and produce some kind of a function and produce theta of k, and then send it to the server. Okay, only the red solid line sends it to the server. Then what does the server do? It collects all the models that it has received so far, including the models it received long time back, possibly, and the ones which it received right now, fuses it with its own previous estimate, and produces a new update. And then that new update need not be sent to the same device, it could be sent to other devices who are active in the next round. Okay, so those are the only types of functions that are allowed. Okay, in at least in this in the federated the federated world. So what is our figure of merit? The figure of merit is you fix a model theta t, which is something the server has after t rounds, and then this is the sum of the losses. This is the global loss. This part of it is the loss as though you would have done if you had pulled all the data and trained on the server. So this is the pooled data loss, and this is the data loss through federated learning, and we call this regret, or the difference between them, as R of t, which is the error between the federated loss minus the loss, if minus what the loss would have been if you had pooled the data without, privacy. Okay, and what do we want to do? We want to minimize this, but we want to minimize not just that, we want to minimize the number of communications required to receive, to make a target error smaller than or equal to epsilon. So fix some target error epsilon. I'll tell you what this expected value is. Fix some epsilon, and you want to figure out what is the minimum number of rounds required to make that target error smaller than epsilon. So what is this expectation? Remember that devices are going to be randomly active. So in this particular talk, we are going to assume that every device is going to be IID active. Okay, it could be very small, but it doesn't care about some other device being active or not. It decides to be active or not active, independent of all the other devices. So that is the model, and this is the expectation that is taken with respect to all the randomizations of the activity. Of course, the challenges to make this happen is that you have heterogeneity, which means you have lots of missing classes, imbalanced data sets, and the participation is the level of inactivity, right? All of these matter in terms of the scaling law for how T epsilon scales with itself. So I was talking about, I think your question was, how do I generalize this idea to multitask setting? So this picture is about CIFAR 100, simply as a cartoon picture of what is going on here. You have different classes. Some of them may be interested in some classes. They may have data about other classes, and so on and so forth. And how can the solution to the vanilla federated learning help you solve this type of a problem? So the core of federated learning, in some sense, if you think about it, it is consensus. So in somehow you want to collaborate with all of the devices in a fashion so that there's an underlying model that comes out which everybody agrees on. Okay, so we want to somehow to do the same thing here, even though we want to customize it. How do I get at something shared that everybody can use, and yet they can modify it for themselves? So this consensus idea is at the root of this solution. Okay, so let me go on. So here is a particular example of how, for instance, different individuals could have different losses. WC of K is the weight for class C of device K. So in the sense, this person may care only about airplanes, in which case WCK will be 1 for this user, for this device user, for the class airplane, and will be 0 else, and so on and so forth. You could have arbitrary weights, but the system is not supposed to know. It's agnostic to what you care about. For the purpose of analysis, we can look at this type of a metric, that is the personalized device loss. Okay, and then you can add up all the personalized device losses to get the total loss. Okay, so the average personalization loss is the sum over all the different devices. So how can we adapt the vanilla federated learning solution to the customized federated learning? If we were to simply optimize per user, the whole problem will decouple, because you have your own model theta k for user k. And if I were to minimize this expression, you will end up with your own particular theta k, which has nothing to do with some other person's, some other device. So the key concept here that we are going to use is there is a common global model or a common representation, which is locally adaptable. So how do we do this? We say that there is a model, underlying model theta, and a transformation, which is tk, adapted by the user. So the k is the user, tk theta is a model transformation that the kth user takes that theta and adapts it for that particular user. So all possible models can be represented in this fashion. That is the assumption that we are going to do. So you get a consensus on some theta, and then locally transform it using this function tk. Now, what can tk be? Tk could be just a gradient descent. For instance, it could be very general. It could be a gradient descent with the data that you have. It could be, theta could be a representation, and tk could be some other kernel machine trained on your data. Whatever, it can be quite arbitrary, but it has to respect the fact that it can only use your own private data. Whereas theta can sort of be sort of used, you can use everybody's collaboration to come up with it. Okay. So if you were to agree on this, then what happens is this PDLK PK is just another device loss. It's just another special device loss. It's just a composition of two functions, which is PDLK and PK. And then that gives you, you can call that your LK. And then theta is something that you agree on. Okay. So at this point in time, maybe I can just sketch different kinds of things that we have talked about, right? So theta star here is the best pool data, and then distributed learning involves this goal, which is minimize overall. My notation was bad. I think in the previous slide I used tk to represent a function, but here this is just the time. So the minimize the number of rounds to make this target regret smaller than epsilon. And when you have no personalization, you're looking for matching this theta star. When you have personalization, you can do a self modification here. Every person has the theta star k, and then you are comparing yourself. Online prediction, you can do the same thing. Here, what is happening is you are in a streaming mode, and in the streaming mode, theta t itself is changing. So every day, theta t changes. So it's somewhat like federated meta learning. You can think about it. Okay, and then you can have personalized meta learning. So lots of different problems of this nature that I talked about a few slides ago. So let me give you a research timeline of what has happened. There's been infinite amount of works on this topic, so I will not be able to do any justice on all the nice contributions. So let me start with what I think are high-level contributions. So this federated averaging, the term federated averaging came about in AI Stats 2017 paper by Brendan McMahon and his group. And here they talked about their definition of federated learning, which is pretty much what I talked about in the very beginning. Then there was this FedProx algorithm that was attempting to get at more a theoretical analysis of Fed averaging. So they developed this FedProx algorithm. This produced, so here there was no definition of FL, but there was no analysis. They gave an analysis in 2017, but what they had to impose serious constraints on heterogeneity, pretty much making all the different users have similar data. So that's what heterogeneity control. And then they came up with a very good gradient descent type of a bound, which was order 1 over t to get your target error. So if I have t rounds of communication, your error would be of the order 1 over t. Then there was this paper, Scaffold, by Google and Google group. What they did was they did a gradient correction, but what they required was they required doubling up the amount of transmission from the transmitter, from the server and the devices, and they could produce this type of it. So in 2021, pretty much 2020, we put our paper up in 2020 around their time, but our paper was published in ICLR 2021. And here what we did was we went back to federated averaging exactly the same amount of bits transmitted per round and arbitrary heterogeneity, fully heterogeneous, no extra transmission, and arbitrary amount of participation ratios. Okay. Now, there was later analysis showing whether federated averaging works. It gives like a rate of 1 by t to the 2 over 3 and so on. And then people went back. Actually, this topic has been studied for quite a long time in terms of distributed learning. It's just called differently in 2014. And so there was this paper, Dane paper. But one big difference between these later papers and this paper was that they required everybody to be participating. It was synchronous and everybody had to transmit, and every device had to transmit all of it. And they also had more bells and whistles like extra states and things. So there is also this work on this decentralized SGD, and then there is a lot of works on variance controls like SVRG and Saga and things like that. But those cannot be easily adapted to the federated setting. But this decentralized SGD could be, but immediately you get a magnification of the rate, okay, to 1 by square root of t. Then yeah.
So since you touched on this, I'm going to ask you to say a few more words about this. Because when I was finishing grad school, I remember hearing that there were all these papers coming out on like all the systems people were suddenly doing like machine learning, and they were like, oh, we can put the data on different machines and do training. And they were basically just doing SGD with some synchronization. And then I didn't hear, and then I kind of stepped away from that area. And then all of a sudden, like in 2018, right before the pandemic, I heard about, oh, there's this thing called federated learning. And we're thinking like, this sounds like very familiar to what I heard about 6 or 7 years ago. What was the big thing that federated learning, this new terminology, added to the mix? Could you give a little bit of just a few words of historical context here? Because
yeah,
I've been puzzled by it.
So SGD, right? Strictly speaking, SGD, you're allowed to, each device becomes a gradient supplier. Meaning the server asks me to produce a gradient on my data, and I produce a gradient and give it back to the server. Federated learning says, hey, wait a minute, you El Cheapo device, you should be doing more work. So the federated learning is about each device doing a lot more gradient steps, almost running a neural network training on the devices, and then giving back the answer to the server, rather than doing one SGD step and doing that.
So you're saying it never occurred to people that you didn't have to synchronize in every update? That was just an idea that hadn't.
No, it's not just about synchronization. SGD, you don't need any synchronization. I can just randomly pick up a device, but only ask for it to compute a gradient, even on one sample, not even in the entire thing, and give back the gradient. And it works. It's just that its rate is very bad, 1 by square root t. I mean, the number of rounds you have to do just because of the stochastic noise in doing only one round of this and not doing a full gradient descent. Immediately gets you to the rate of 1 by square root.
Wasn't there also just an element of like asynchronous that came with federated learning too? Like I think before.
Sure. The asynchronous business also, I think Jake would say that, oh, give me a break. Asynchronous was somewhere hidden in these papers as well, because, by choosing samples at random and only updating with those samples, that is kind of asynchronous, right? I think the main difference is, at least Brendan talks about this difference extensively in this paper. And the main difference is that federated just means that the device does some heavy lifting. Device does heavy lifting, not the server. Server doesn't do any work. The device does all the work. So you would run the whole neural network training on the device and then give back the answer.
And I talked to Brendan about this in 2019, and I think the impressive thing there was that they were actually doing this in Google on people's phones.
Yes.
Right? It was like text prediction was actually being done this way and implemented effectively. That seemed to me like that was the big advance. I didn't know. I was like, isn't this happening about this before? I was like, no. The devices are actually doing this, and it's actually helpful. But I didn't know about the sort of synchronization issue was somehow relevant. I thought, because in some sense, they also are asking for gradients here too. Federated learning are asking for gradients. You just do several gradient steps first, and then you kind of.
Not only several gradient steps first, you will run it like you train a neural network on the device with your data.
Just a sequence of gradient steps.
But immediately the proof doesn't work anymore. The minute you start running a lot of gradient descents on any one device, then you entirely bias the model. And so even to prove that it converges is a headache. And so that is the reason they had to impose these types of heterogeneity controls and so on. So instead, if you were to do pure SGD, right, then what happens is I randomly choose a device and randomly choose a data point inside the device. That's like SGD. That's no different from SGD, because double randomization is still randomization. By choosing a device and randomly choosing a data point in the device is the same thing as choosing a data point at random. Rather than that, in federated learning, you choose a device and run a neural network and train the whole neural network and then produce a model, and which is then given to the system. Anyway, so then after that, there have been a lot of papers, but by and large, most of these papers either assume full participation, meaning everybody should participate all the time, or other types of schemes where they do a switch, and then when the switch is on, everybody participates, and then you turn the switch off and nobody participates. This kind of various schemes have come up, but not like this random participation, anybody can participate type, like this line of papers have been talking. So let me explain this federated SGD method. So you have this loss, you have this empirical loss, and then what is the federated SGD method? Exactly what I was talking about. You take your cloud model theta naught, do one gradient step of your local device, and send it back to the cloud. And what does the cloud do? It just takes the average of all of these models. I guess the reason I've been going back and forth is because my mouse is invisible there. Anyway. So you take the average of all your models and give it back to these devices. So this is very simple thing. Yeah, so the Fed SGD is that. Just SGD is not that. The Fed word at least allows you to do one gradient. Okay. So does it work? What did I do? I drew this pretty picture simply as a way of explaining what is going on. So what are these pictures? Think of these as quadratic losses. This orange device has its minima at this place, and then the black device sorry, there are 3 devices, device 1, device 2, device 3. Green device has its center here, device 2 has its center here, device 1 has its center here. The optimal is here. So what happens with FedSGD is you start somewhere, you walk a little bit because your learning rate only allows you to walk a little bit. Why do you walk that way? Because this device became active. So you walk a little bit that way. And then this device became active. So you walk a little bit that way. And the blue became active, you walk that way. And then you're marching along little by little by little. Okay, so eventually it does converge to the correct answer. But this correct answer, the latency is 1 over epsilon squared. So it takes a very, very long time to converge. We don't like 1 by epsilon squared, we like 1 by epsilon. Okay. So convergence is slow and communication rounds and latency is high. So what did the federated learning guys do? This is the McMahon's paper. What they did, and then the FedProx was a paper by Talwalkar, who is now at CMU, and Virginia Smith. And what did these guys do? They said, hey, in federated averaging, each client or each device should do more work, which means that you run for I equals 1 to k, for each active device, you run this many times. So you run this many times, and then you update the model and give it back to the server. But the server just, again, averages, doesn't do anything fancy, and gives it back to the device. Okay, here what happens is kind of interesting. Now that you do lots of different updates per device, you make a big move. So you start here, you make a big move towards orange. Here, you again make a big move towards the green. And then the blue shows up, you end up making a big move towards the blue, and so on and so forth. Okay, and this happens. And why I have drawn these devices in different places is because they have different data. So their minima are in different places, right? If I had pooled the data, this would have been the optimal thing to go to. But if you just optimize the green, you would have ended up in this. So you cycle around, you keep cycling around, and you may never converge unless I impose very strong conditions on where green, blue, and orange are. They have to be close to each other. If they're not close to each other, then you could just not converge at all. Or you might take a very, very long time. Okay, so is this clear? Okay.
So I have a question. So when you say that you need distance to be small between the tasks, what is it small?
So the distribution, the precise definition would be that the loss functions, the variance of the loss functions, as you take across the different devices, that variance of the loss should not be too large. There has to be a bound on the variance, some strict bounds on that variance.
And is it with respect to the parameters for a number of iterations?
No, this is a priori assumed. So you a priori assume that take the loss function L theta and then take the variance of this L theta. L theta is empirical. And so variance of L theta will give you some number. And then as a function of theta, it has to have certain properties. And the variance itself has to be uniformly bounded. These kinds of things you have to impose.
Right. But when you say small, it has to.
I mean, if it is small, so you have results which say that if it is B large, then you will get a scaling factor which is related to B, and it gets, some papers even have worked out formulas which, as we know in machine learning, many of them are vacuous. So it gives you things which are absurd, like probability of error bounded by things greater than 1 and so on, right?
So you're converting basically you're converting to a ball on the optimization. It really is that depends on this concept. But final problem is looking like the submodular optimization.
This one?
Yeah.
Why is it submodular?
It's like suppose each device has
Yeah.
Yeah, so you have those kind of maps, or you just think it's
I don't know whether it's related to submodular optimization. Maybe we can talk about it later, but I don't see a direct connection to submodular optimization.
I have another question.
So if the distribution of data in each device are different from each other way around, but we have to synchronize it.
So let me actually give my solution before we come back. I think I have many more slides. So can I skip and come back to your point? Sorry. I think we started late, so I'm allowed to take a few extra minutes. Okay, so what is our solution? Our solution is the following. So Fed averaging a Fed prox locally is trying to optimize this kind of a function. Its own personal loss, LK theta, plus some kind of a regularizer which says I should not be too far away from my cloud model. So theta naught is your cloud model. I should not be too far away. What that means is that if I'm here, I still take a biased direction. I go from here towards this thing because I don't go very far from my theta naught, but yet I go towards the bias, right? By minimizing this. Now, in reality, I should have gone in this direction, which is the sum of the gradients of everybody. So the average of the sum of the gradients of everybody, that is the direction I should have gone. So this is the H is the direction I should have gone. Instead, I'm going in this direction. So the oracle direction is that guy, and I'm going in the wrong direction. So we want the global gradient, want it to be 0 eventually. So what can we do? Let's say we are allowed to construct this fake loss. What is the fake loss? There is the loss minus some linearized version of debiasing, which means that take this, you simply subtract away the Taylor series, first order Taylor series expansion from your device loss, add back the true gradient, which is this guy, which would have been evaluated if you could, and then do the same regularizer that the Fed prox was doing. Now, none of this is true, none of this can be done, but supposing one can do, then it does turn out that if I were to take a gradient step of this objective, you will indeed, I mean, it's not very surprising, you will go in the correct direction, right? So like our entire idea rests on how the heck to make this happen in an easy way, such that without increasing the computation required or without increasing the messaging required. So in any case, so let's start thinking about this, how to debias distributively. So we have this fake direction, how to do it in a distributive way, okay? So the problem is this true direction H is unknown to the device. So first of all, can we massage this equation using completion of squares and write it in a way that makes it easier at least to take some baby steps. So one thing that you can notice if you have done any completion of squares is that this third term and the last term can be combined to write it in this way, and that doesn't change the optimization problem. This is just the completion of squares. Now, interestingly, theta naught minus 1 by alpha h could be thought of as something the server could have pre-computed and sent, rather than asking the device to somehow figure it out. So supposing we push all of this work to the server, which is saying that, hey, server, don't send me a cloud model, but send me a corrected model, which is theta naught minus 1 over alpha times h. So let's call that theta prime, okay? So if the server could somehow send this model, rather than sending the model theta naught, then we are done. Then the local device just subtracts this Taylor series expansion and does a regularization not with respect to theta naught, but this corrected model theta naught minus 1 by alpha. So that's basically what the solution that we want boils down to. Okay, so now we have, instead of theta naught, we have theta prime. Okay, and then you have this new objective. Remember, this objective is going to get modified every time you do an update because you're solving a new object. So the question is, how can the server compute H? Here, an interesting fact about optimality conditions is that the gradient difference is exactly for the local device. The gradient difference turns out to be the local and server difference actually. So how is that? Supposing I take a derivative of this and set it to 0, then the derivative of this minus the previous derivative is exactly proportional to the difference in the models itself. So theta k minus the cloud model is proportional to the difference in the derivatives. Okay. So why is this important? It's important because the server has difference in models. Because I sent the model to the cloud, whoever has sent, it has all those differences. So since it has all those differences, it can compute those differences, pre-compute those differences based on the models it has received, the server, I mean. And then it can maintain an update. And it's not very hard to see that if you just telescope this, you'll end up with the sum of the gradients of the models. Now, the important point is this is not still this guy, because here theta k is now a function of t and a function of k. Here we wanted a gradient evaluated at a particular model. So there is still a difference, but you can get at what we are, if we can somehow plug this in instead of this and show everything works, then it all works. So that unfortunately requires a little bit of work, and in the interest of time, I'm going to skip that. But basically, that's the idea. You remove, you debias it, and you allow the server to correct and send you the correct answer around which you sort of have to do your gradient descent. Okay, yeah.
So every user kind is gonna have different
Objectives.
Yeah, it's gonna have different gradient track. Each server is gonna give different gradients to each of the client, or the debiasing is going to be common for.
No, debiasing is not common to every client. Has its own debiasing because it has a different distribution. So it debiases differently. The only thing common is what the cloud gives the devices. The cloud gives a common model, but it gives a corrected gradient model. Corrected its own model minus its estimate of the gradient. So you can use that to debias yourself. But the way you debias yourself is different for different. Right. So anyway, so I've explained this procedure. So you take everybody who is active, compute these differences, and that gives you an estimate of the gradient. And then you also have a model update locally for the server. It does not send that model, but it sends this corrected model. And that corrected model then goes to each one of these devices, and then they do a dynamic regularized update individually, and then send back the answer. Okay. So does that work? Indeed, it works like magic. So, so basically, when you have this, it really converges quite quickly, this correction, and we can show that essentially the proof boils down to somehow showing that this is like a fixed point. Okay. This whole global thing is like a fixed point, and proving that the convergence rate is quite good. So the reason I mentioned fixed point is because once it gets there, that is the solution, and it does not diverge away from the optimum solution. And then we proved all kinds of rates for this. Here is something that we proved: the number of the latency required to get to epsilon error scales as square root of m by s times 1 by epsilon. Now, what are these things? S is the average number of active devices at any round. So expected number of active devices any round. Remember, I assumed an IID model. So you are allowed to plug in an expected value, which is not changing over time. And then M is the total number of devices. Square root of m by s is like the participation ratio. So you have the gradient descent level convergence rate with respect to the target error and t. And then you have the square root of m by s, which is the participation ratio. Now think about it, right? if M by S is, you can have many more devices than the number of rounds you run for, and yet this gives you a reasonable answer. How can that even be possible? And the reason is the cheating going on in terms of taking an expectation of the regret rather than bounding it with rather than taking the variance terms. Okay, so that is why even without looking at all the devices, I'm able to produce a bound which is even better than looking at every device's data. So
this IID assumptions, when this IID are you assuming so each device has equal probability of activity, or
yes.
it's like some devices are more active, some are less active? Because
so that is an entirely another field of federated learning, which is called objective inconsistency or objective consistency, something it's called. And that's a mess basically, because now you let every person be active different amounts of time. What really should I consider you important or not important? But the bottom line is, as long as our proofs will work out, as long as we are within a band of activity, meaning you cannot let some users go to zero. They're like never active after like transition period, they're active first square root of t rounds, and then they'll never be active. Right? If you have such scenarios, things don't work out. But if you have like an infinitely often type assumption that everybody is, comes on infinitely often in an asymptotic sense, right?
I was just thinking that in the gradient computation, when the gradient is average of everything, so is that where the IID assumption is sort of being used when you want the edge term that you're using is basically average gradient over all with equal weight? So is that where the IID assumption sort of?
No, yeah, the IID assumption actually is in translating. Here you're going to get only the active devices, but when you want to hit it with the expectation, you want to sort of get the true expectation, right? So that's where the unbiasedness is going to happen. But if you don't have, if you still have IID, you will get some other jump, which will be the weighted sum of these loss the gradients. You can correct for it by doing like it's actually like an importance sampling. So you can invert everything, but then that is where the zero business comes in. So if some devices are never going to be active or whatever, and you're going to blow up that person's weight by humongous amount, and then the analysis becomes a little bit more. Okay. So you can also do this for non-convex setting, except that we are now going to converge to a stationary point rather than the optic, right? And then we have this relationship. By the way, this for the convex case, this is the optimal you can get. You can actually prove lower bounds that show that you cannot do better than that. And the important thing also is that this whole scheme does not require any extra amount of information from what federated averaging was. So the same amount of information transfers back. So here is, I have a lot of slides, so maybe I can just skip everything and show you some pictures that it does work on real examples that may be better, right? So here are some things that we set up. Here is an experimental setup where you have a vision data sets, MNES. These are benchmark data sets people use in federated learning. Here is a language data set. Amazon is super interested in these kinds of things. And then the architectures, we basically use very small neural networks, not because we can't train bigger ones, just that these have become the benchmarks. So you just have two convolution layers, like a Linnet type machine learning model. Okay, for the language, we had these stacked LSTMs. Cool. And then we had different types of evaluation criteria. For data heterogeneity, what we did was, we did this thing called Dirichlet process, where you would, for some devices, to get different distributions for different devices. So maybe this if you haven't heard of Dirichlet thing, no matter what I explain is not going to help you understand it. So I'm just going to skip that. Basically, the point is you want to get different distributions of data at different devices. Okay, and so you do this kind of a thing to calibrate how much data heterogeneity you produce. Okay, and then you measure all of these things based on how much communication rounds you needed in order to get some level of performance. So the interesting part is our debiasing step actually gets you to a much higher performance than those competitors. That is one thing that you notice. Of course, we are winning quite a bit in these communication rounds. And we also notice that this performance that you get has no bias with respect to pooled data. That is, even though this is a non-convex world, we train it in this way, we end up getting for like IID, this is like similar distributions everywhere. You get the same performance as though you had pulled all of the data and trained it. So 85% is the maximum. You will eventually get the same performance using it without losing any privacy. Now in the non-IID world, it is not quite that clear because your performance is a little bit smaller. We will take a lot more rounds to get there, but we will eventually get as well. So we did a lot of experiments with many data sets, for 10, for 100. The performance are uniformly. So I'm not cheating by doing one data set and not showing you only the best results. So across the board, it does do much better than all the other competitors, right? The thing here is the number of communication costs. So how many more rounds do you require? We scaled ours to 1 with respect to us. How many more do the others require? I'll say one more interesting experiment because I think it's interesting. This is a personalization experiment, which is we now have not only select different data sets for different devices, but we also select which classes different devices are interested in. Okay, so some may be interested in airplanes, some may be interested in houses, and so on and so forth. So, and then we did this experiment, which is anonymous. We call it anonymity of content. What that means is every device is allowed to call an airplane a bird, or a deer a cat, or something. It doesn't have to reveal what real images it has. It doesn't have to. It just can label it any way it wants, as long as they are distinct. And then it sort of, this whole federated learning setting happens. And we wanted to figure out how it performs with this anonymity. Okay. And again, we can see that that does not impact our performance, whether we take correct class association or incorrect ones. Incorrect ones we lose a little, but yeah. So maybe I should stop. I'm way over time. So in conclusion, I think I've talked about a whole bunch of things. The two things I didn't talk about, I think the main thing I didn't talk about is this exact idea what we used it to do memory efficient meta learning. In meta learning, what happens is you are given new tasks every day and you have to adapt to that task. And then typically meta learning remembers everything that you have done in the past, so it's not efficient. So how can we use this debiasing idea in order to do meta learning? So that is something. So there are some other ongoing projects. We have a project on hybrid edge where there is a server and a edge device, and the edge device could be like as small as an MCU unit. How can I do ImageNet level classification on this MCU? Well, you cannot. So what that means is you will have to reject a certain or abstain and ask the cloud to make those. So what are the fundamental trade-off curves? How much of ImageNet classification can I do locally? Can I figure out which examples are easy for me? So that is that type of work. We have a paper on bandit change detection. So there you have multi-sensor monitoring systems, and you want to figure out something change happens in one of those sensors. You don't know where. The sensor is like a location, and you are allowed to select only one sensor at a time. And the question is, can I come up with a policy that gets you to the optimal sampling of the optimal sensor, the correct sensor, as fast as possible? Then obviously this whole idea of learning with safety constraints, this is a more recent topic that I've gotten interested in, where you may have a drug and the drug has efficacy and it can cause you lots of side effects. And the problem is to select the right drug and the right dosage so that it gives you a certain level of best possible efficacy with the constraint that its side effects are not too large. So how do you go about adaptively sampling in order to do that? And our main idea here is to face not uncertainty, I guess, face safety with optimism. So you say, oh, even if things are unsafe, you need to try a bit. And that leads to some interest in it. Okay, thank you.
We have a lot of topics, so there's no need to force the issue, but if there's a pressing question, we can take one to wrap this up. Okay.
So what is the concept of adding linear terms to the law so that So what is the advantage of adding a linear term to the loss?
Subtracting a linear.
Yes.
So if I take if I do a Taylor series expansion of the loss, the previous loss plus the gradient with that Taylor series. Okay, so that is the bias because your gradient descent is going to go towards that particular losses minima if you keep doing that. And in all the federated learning work, that's what you will keep doing, and that eventually will reach the minimum of your own demand. By subtracting it and adding back this approximated gradient, you are debiasing yourself by forcing it to not go there, but and get benefit from that.
So is that like better than like scalable method?
It is, yes, it is. I mean, scaffold doesn't do exactly.
Thank you.
All right, so we have any question from online audience?
All right, Fair Mars.
Yeah.
You can come on, Fair Mars.
Hi, Venkat. Thanks for
Right.
interesting talk.
Is
The
that
question-
voice? Did you have
Do you hear me?
the sound?
Yeah, I can't.
You have to.
You hear me?
Turn up
fine?
the
Right, the mic, the speaker.
Unmute.
You have your speaker?
Yeah, I have my.
Is
Otherwise,
that okay?
All right, now, yeah.
We can.
Yeah. So thank you for interesting talk, Venkat. I have one question. You talked about this personalized federated learning. I'm curious, this personalized federated learning comes at the expense of convergence rate or not? Can you comment on that?
It does not. So okay, so I have the mute. Oh, I see. No. Okay. So am I audible now?
Yes, I hear you, Venkat.
Oh, he can hear me. Okay.
Is your speaker open?
What you could do is you and Fairmarsh catch up.
Yeah.
I can hear now. If
Fairmarsh,
Yeah.
can you stay on for a second? Okay, we'll figure this out. Let's thank the speaker. Thank you, Rocco. Thank you to all of you for moving it along by asking some interesting questions. I think it helped a lot. Actually.
Pizza Hut.